Ever pondered on the strange origins of complex numbers? Let's take a journey back in time to the birth of this intriguing concept. The tale of complex numbers begins with the ancient Greeks. They were the first to grapple with equations that lacked real solutions. But like a puzzle with missing pieces, these equations left the Greeks scratching their heads. Fast forward to the 16th century, and we find ourselves in the company of Girolamo Cardano, an Italian mathematician. Cardano took a leap of faith into the unknown, daring to formalize solutions to cubic equations. In the course of his work, he stumbled upon the square roots of negative numbers. This was a mathematical conundrum, a paradox that defied the existing knowledge of numbers. In an attempt to make sense of these strange roots, the term imaginary was coined. Although the name might suggest otherwise, these imaginary numbers were about to become very real in the world of mathematics. They formed a cornerstone for a revolutionary concept that was yet to come: the complex numbers. Complex numbers, as we know them today, are a blend of the real and the imaginary. They challenged the traditional notions of what numbers could be, shaking the very foundations of arithmetic and geometry. And with their introduction, the mathematical landscape began to change, opening up new vistas of understanding. The complex numbers were like a new language, allowing mathematicians to express and solve problems that were once thought impossible. They were the key that unlocked the door to a whole new mathematical realm, a realm that was as beautiful as it was baffling. Thus, the fascinating journey of complex numbers began, challenging the traditional mathematical notions. And as we'll see, this journey was only just beginning. The world of complex numbers was about to become even more intriguing, revealing patterns and connections that continue to captivate mathematicians to this day. Complex numbers, as their name suggests, are indeed complex, but what makes them unique? Diving into the heart of this question, we find ourselves in the realm of the complex plane. This is a plane where real and imaginary numbers coexist, each occupying their own axis. The horizontal axis represents real numbers, while the vertical axis is home to the imaginary ones. This plane provides a visual representation of the intricate world of complex numbers. Imagine a number as a point on this plane. Its real component determines its left or right position, while its imaginary component decides its up or down location. In this way, every complex number has a unique place in this plane. This property allows us to visualize and understand complex numbers in a two-dimensional space, an advantage not available with real numbers. But the uniqueness of complex numbers doesn't stop there. They also possess a property called conjugation. The conjugate of a complex number is another complex number with the same real part, but an imaginary part of the opposite sign. This might seem like a small detail, but it has profound implications on the behavior of complex numbers, especially when it comes to multiplication and division. Now let's talk about magnitude. Every complex number has a magnitude, also known as its absolute value or modulus. This is calculated as the square root of the sum of the squares of its real and imaginary parts. This property helps us understand the size of a complex number, regardless of its position in the complex plane. And then there's the fascinating interplay between real and imaginary components. This interplay often results in beautiful symmetries and patterns, revealing a deeper understanding of mathematical structures. It's like watching a dance, where each step, twist, and turn creates a dynamic, ever-evolving pattern. This dance is one of the reasons why complex numbers are so integral to many areas of mathematics. The unique properties of complex numbers reveal a new, intricate realm of mathematics. The beauty of this realm lies in its complexity, its depth, and its ability to challenge and expand our understanding of numbers and their behaviors. This is the unique and intriguing world of complex numbers, a world full of surprises and insights waiting to be discovered. Numerous mathematicians have contributed to the understanding and development of complex numbers, but who were the pioneers? Let's delve into the work of a few key figures: John Wallis, Leonhard Euler, and Carl Friedrich Gauss. Each one of these mathematicians played a crucial role in paving the way for our understanding of complex numbers today. John Wallis, a prominent English mathematician of the 17th century, made significant strides in infinitesimal calculus. Though his work didn't directly involve complex numbers, it set the stage for their later exploration. Wallis is most known for his introduction of the symbol for infinity, a concept that would become integral to the study of complex numbers. As we move forward in time, we encounter Leonhard Euler, a Swiss mathematician and physicist. Euler's work is often hailed as some of the most groundbreaking in the field. His eponymous formula, Euler's formula, is a jewel of mathematics. It provides a deep and elegant connection between algebra and geometry, bridging the gap between complex exponentials and trigonometry. This formula not only advanced the field of mathematics but also exemplified the beauty of its interconnectedness. Lastly, we arrive at Carl Friedrich Gauss, a German mathematician often referred to as the Prince of Mathematics. Gauss's contributions to the field are vast, but his work in complex analysis stands out. Through his research, he laid the groundwork for many of the developments we saw in the 19th and 20th centuries. Gauss's work further cemented the importance of complex numbers, proving their practicality and versatility within the discipline. These three pioneers, Wallis, Euler, and Gauss, each brought unique contributions to the table, further enriching the tapestry of complex numbers. Their work not only expanded the field of mathematics, but also opened doors to uncharted territories. Their pioneering spirit continues to inspire countless mathematicians today, and their contributions remain foundational in the study and application of complex numbers. The work of these pioneers solidified the significance of complex numbers in mathematics. Through their relentless curiosity and profound insights, they truly paved the way for the complex numbers we know and use today. Complex numbers are not just theoretical constructs, they serve practical applications too. But where do we see them in action? From abstract theories to practical applications, complex numbers are everywhere. Let's start with electrical engineering. In this field, complex numbers are used to analyze alternating current circuits. The real part of the complex number represents the resistance, and the imaginary part represents the reactance of the circuit. This allows engineers to study the behavior of the circuit in terms of amplitude and phase, which is essential in the design and analysis of electrical systems. But the reach of complex numbers extends far beyond engineering. They also play a significant role in the realm of quantum mechanics, a branch of physics that deals with phenomena on a microscopic scale. Here, complex numbers are used to describe wave functions. These wave functions provide a mathematical description of the quantum state of a system, and as it turns out, the probabilities we derive from these wave functions are instrumental in predicting the behavior of particles at the quantum level. Complex numbers also help us in understanding the fundamental nature of the universe. They are used in the field of relativity to analyze space-time, and they also play a role in string theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. And that's not all. In the field of computer graphics, complex numbers are used to rotate images in 2 dimensions. In signal processing, they help to analyze and manipulate signals. In control theory, they are used to design and analyze systems that maintain a certain behavior. In fact, complex numbers are so versatile that they're even used in the field of economics, where they are employed in models that deal with economic dynamics. From the intricate circuits of electrical engineering to the quantum realm, from computer graphics to economic models, complex numbers are a mathematical tool with a vast array of applications. They help us solve problems that would otherwise be impossible to tackle. Complex numbers have a profound impact across diverse fields, proving their indispensable role. The beauty of complex numbers is evident in their capacity to unlock solutions to equations previously deemed unsolvable. But how does this weave into the rich tapestry of complex numbers? Complex numbers are not just about solving equations. They form a powerful algebraic tool that extends their influence across diverse mathematical domains. Their real and imaginary components intertwine, creating a harmonious dance that gives rise to a plethora of mathematical structures and concepts. Take the fundamental theorem of algebra, for instance. It states that every non-constant polynomial equation with complex coefficients has at least one complex root. This theorem, a cornerstone of algebra, wouldn't hold its ground without the concept of complex numbers. It's the perfect example of how these numbers break down the barriers of what we previously thought was possible in mathematics. But the story doesn't end there. The versatility of complex numbers stretches out to calculus, differential equations, and number theory, unveiling a deeper understanding of these fields. They provide a common thread, linking seemingly disparate areas of mathematics into a unified whole. And then there's the world of fractal geometry, a realm where complex numbers truly shine. Here, iterative processes give birth to intricate, self-similar patterns that are as mesmerizing as they are complex. The most famous of these fractals is, of course, the Mandelbrot set. Generated through the repeated application of a simple formula involving complex numbers, it creates a visual landscape that blurs the line between art and mathematics. It's a stunning testament to the intersection of the visual and the abstract, brought to life by the power of complex numbers. From their historical origins to their applications in cutting-edge scientific fields, complex numbers stand as a testament to the interconnectedness of mathematical concepts. They weave a vibrant tapestry that stretches across the entire mathematical landscape, adding depth and richness to our understanding of the universe. As we continue to explore this tapestry, we don't just learn more about numbers, we discover the profound beauty that lies at the heart of mathematics.